So today, we're going to tackle a really beautiful mystery, one that helps shatter classical physics and drag us into the wonderfully strange world of quantum mechanics. The question is, why do atoms only shine in very specific, discrete colors?
Okay, let's start with what we all know. You see a rainbow or maybe light shining through a prism, and what do you get? You get this beautiful, smooth, seamless spectrum of color, right? Red just kind of melts into orange, which melts into yellow, and on and on. That's light as we see it every day.
But things get really weird when you look at individual atoms. If you take a gas of a single element, say hydrogen or neon, and you heat it up, you don't get a rainbow at all. You get this, a set of sharp, individual lines of color. It's like a barcode, and every single element has its own unique barcode.
Now you can imagine for physicists back in the 19th century, this was a huge problem. A complete crisis. According to their rulebook, an excited atom should be glowing in a whole smear of colors, all the wavelengths. But it doesn't. So what's going on? Why this strange, very specific language of light?
To really get why this was such a revolution, we first have to understand just how badly the old rules, classical physics, failed when it came to the atom. I mean, it wasn't just a little bit wrong, it was spectacularly wrong.
So here's the deal. The classical model of the atom was pretty simple. You have a tiny electron orbiting the nucleus, kind of like a planet orbiting the sun. But this picture had one absolutely fatal flaw. According to the laws of electricity and magnetism, an orbiting electron is an accelerating charge, which means it should constantly be radiating away energy as light. It's like it's bleeding energy. And as it loses energy, it would spiral inwards and, boom, crash right into the nucleus in less than a second. Classical physics basically predicted that atoms shouldn't exist.
And this wasn't some little detail they could just sweep under the rug. I mean, Niels Bohr himself, writing in his huge 1913 paper, basically said, hey guys, the fact that we even exist proves our physics is fundamentally broken at the atomic scale. Something totally new was needed.
And that new idea came from Bohr. He didn't just try to patch the old model. He proposed a completely radical new set of rules for how the universe works on a small scale.
Bohr's solution was, well, it was kind of nuts for the time. He just flat out declared that some parts of classical physics simply don't apply. He said, okay, rule 1, electrons can only be in certain allowed orbits, each with a fixed energy. They can't be anywhere in between. And rule 2, they don't spiral, they jump instantly from one orbit to another, and when they do, they spit out or absorb one single packet of light, a quantum.
And just like that, bam, the whole barcode thing suddenly made perfect sense. The color of the light, its energy, corresponds exactly to the energy difference between the two orbits. And since only certain orbits are allowed, only certain jumps are possible. And that means only certain colors of light can be produced. For the very first time, the barcode for hydrogen wasn't a mystery anymore.
But here's the thing. As amazing as Bohr's model was, it wasn't the whole story. It was more like a brilliant hack. The full, and frankly much weirder, picture came about a decade later, thanks to Erwin Schrödinger. So Schrödinger comes along and just blows up the whole idea of these neat little planetary orbits. He shows that electrons aren't tiny planets on tracks at all. Nope, they exist as these fuzzy, three-dimensional waves of probability. These shapes you're seeing here, they aren't paths. They're called orbitals, and they're just the regions where you're most likely to find the electron.
Now this is where it gets really, really cool, because this wave-like nature of the electron means it can't just jump wherever it wants. Nature has, well, it has rules of the game, and we call them selection rules.
This diagram for hydrogen shows it perfectly. Think of these selection rules like a bouncer at a club for electrons. Nope, you can't jump from that orbital to that one. These rules come from deep principles, like making sure angular momentum is conserved. And that is why we see only these very specific lines in the spectrum and not just some chaotic mess of color.
Okay, but the rabbit hole goes even deeper. Because if you take a really powerful instrument and you zoom way in on one of those spectral lines, you find out it's not actually a single line at all. It's made of several, even finer lines, all packed together.
This first level of splitting is what we call fine structure, and it's caused by this really subtle effect that involves Einstein's relativity. It's basically an interaction between the electron's own spin, it acts like a tiny magnet, and the magnetic field that gets created by it orbiting the nucleus.
And when I say subtle, I mean tiny. Look at that number.
The energy difference is just incredibly small, which, is why we call it fine structure. It's this minuscule little correction, but it's absolutely beautiful because it's proof that to get the full picture, you really do have to bring both quantum mechanics and relativity together.
But we're not done. We can zoom in even further. There's an even tinier split, and this one's known as hyperfine structure. This effect comes from the electron spin interacting with the spin of the nucleus itself.
Let's just take a hydrogen atom. You've got an electron and a proton, and both of them have spin. So their spins can either point in the same direction, we call that aligned, which is a slightly higher energy state, or they can point in opposite directions, anti-aligned, which is a slightly lower energy state. This tiny difference splits hydrogen's most basic state into two incredibly close levels.
Now, what happens when an electron in that higher state spontaneously flips its spin down to the lower one? Well, it emits a photon. And because that energy difference is so unbelievably small, the photon it spits out has a wavelength of 21 centimeters. That's a radio wave. And this one single hyperfine line, well, it turns out to be one of the most important tools in all of modern astronomy.
So after all this deep dive into quantum jumps and tiny energy splittings, you gotta ask, why does any of this really matter?
Well, these atomic barcodes are basically a cosmic Rosetta Stone. Seriously, because every element has its own unique spectral fingerprint, we can point a telescope at a star millions of light years away and tell you exactly what it's made of, without ever leaving home. It's incredible. And that 21-centimeter line? Radio astronomers use it to map the vast, invisible clouds of hydrogen that trace out the spiral arms of our very own galaxy.
So you see, the sharp lines of light from an atom aren't just a curiosity. They are direct, in-your-face evidence that reality is quantized. They were the clues that forced us to see that the classical world was incomplete. Every neon sign, every star you see in the night sky is broadcasting the fundamental laws of physics, all written in this beautiful language of discrete lines.